thank you everyone for joining us for this week's Power Hour. We are going to be going over Greenheck's centrifugal fans, fan arrays, blower styles. As normal, we have everyone muted. Please put all of your questions in the chat and we will do our best to moderate as we go. We may hold some of the questions at the end, but if it makes sense, I'll interrupt Elizabeth as politely as I can, and we'll get the question addressed. Anything you see here, we're happy to do individual presentations for your firms, or on a project specific or just a general presentation. As always, today we have Blake Bonham, our sales engineer out of our Spokane office, with a salute. Nick Andrews, our newest sales engineers out of the Seattle office, and then our fearless leader, Scott Boucher, who's not on right now, but he might pop on at the end if he graces us with his presence. With that, Elizabeth, I'm going to let you take it away, and I'll just keep an eye on the chat and let you take over.
Sounds good. So thanks so much for the invite, Chris. I'm Elizabeth Krieger. I am with our centrifugal fan team here at Greenheck. Behind me, I actually am in our innovation center. That's our test center. So if you do ever get to visit, you'll get to take a wonderful tour, check out some of our test chambers, see what we have going on. So we'd be happy to have you. With that, before I jump into the prezo, if you guys have any specific application questions, like that's what I'm all about, because it's like you might know these fans exist, but what do you actually use them for? Like, what do you actually use blowers for? Where are you going to put these fan arrays going forward? So if you want to put any application questions in the chat, we'll definitely try and focus on those and get those answered for you. So with that, just going through, we'll talk about our USF, that's our utility set fan, that's our blower fan. The fume jet is actually a component to that. It's like a next step up where we actually have a blower with a stack. So beyond that, we'll go into fan array systems. So all of these fans use that centrifugal style wheel. They all have an inlet cone. So there's only one direction that air can flow with these style fans. So with our blowers, where does a blower actually fit in the market? Like performance-wise, cost-wise, looking at this slide, you can kind of see where we fall. So we're in between that spun aluminum. We're lower level to lab exhaust. We can still do, a built-up system like you can kind of see in that top corner picture. But we're just not to that lab exhaust level. So that's kind of where we see the USF fitting in. So a lot of performance points. So we can hit, again, performance points across the board with these. We can do low CFM, high CFM, but really our target range, if you can kind of look at that chart there, where the green really falls, it's going to be a 10,000 CFM or less, and 2.5 inches of static or less. So that's the range there. Generally, we're kind of equal in selling belt drive and direct drive, and that comes with preference and application. So it's really up to if you're going to need to control the fan or not. You're going to be going direct drive. If you are going to go with controls, belt drive. If it's kind of a one-off application, this is just what this fan does. So looking at where the price points come compared to our competitors. So if you do come across any competitors where they've had, a captive air model on site, they've had a cook model on site, we do have those economy level fans. If you're doing retrofits, this is more for, Chris and our reps to know, but it's a good gauge to show you that we compete across the board, right? We have those lower level fans. We have those mid-level fans and also the upper higher level performance fans as well. So basically here's what the USF can do. It can, like I said, move a little air or a lot of air. They're really good at building pressure, up to 21 inches of static pressure. We can put 150 horse motors on these if we need to. But generally, you know, we'll see between, you know, a half horse to the 7.5 horse range is probably more typical. So these fans are highly configurable. So what that means is we're going to be able to make them out of stainless, aluminum. We can do high pro Z paint. That's the same paint that goes on our Vector fan units as well. So lab exhaust, aka lab exhaust. But again, the typical is less than the 10,000 CFM. It's just going to be a basic painted fan. So as far as our market share goes, we're pretty good with that as far as being top spec'd out in this category for USFs. Our annual sales are right around 13,000 units. So now here's the features that I was talking about. So materials, steel, aluminum, stainless. So the applications for these are across the board. So stainless we'll see used in coastal applications. It tends to, obviously, if you have a steel fan, we've seen degradation on those. So sometimes we actually, for some of our regions, insist on going stainless or at least upgrading to our 2-coat coating on our fans, that high pro Z coating. Aluminum, you can see for moisture laden applications, food processing, and then steel, galvanized or coated, just basic exhaust applications. So we do actually are seeing more of the blowers used for supply as well. Because we do have downblast available. So the downblast helps facilitate the fan still being on a roof and then moving air in for, you know, fresh air applications. We do offer our fans to be put on curbs as well. So what you see here is actually an inlet box. Our contractors really tend towards the curb and curb cap applications because then they don't have to run additional ductwork into that fan. Normally we want to see like 3 wheel diameters of straight ducting leading like into this area here. Oop. Just jumped ahead for me here. So leading to the inlet of the fan. We've actually been through and done testing on this geometry of this inlet box. So any losses that would normally occur, any system effect that would normally occur with this application, we've already accounted for. So really, the contractor or the building just needs to bring its ductwork up to the bottom of that inlet box. We have a duct drop that ties right into their system. So this is available in belt drive or direct drive. We can do isolators in this configuration as well. So isolators, again, just basic background on those. We're going to put restrained type isolators so that if the fan is outdoors, again, all USFs are made to go outdoors. Even though 50% of the applications that I've seen are indoors, they are meant to go outdoors. If they do get put outdoors, we want to restrain those isolators. Otherwise, the wind loads can tip those fans off. So do be sure to choose restrained type if you are putting the fan outdoors. So, and all the fans that you'll see here today, we're offering controls for. Whether it be selectable through our CAPS programming, some of our industrial process fans use really big motors, so then we'll do an SDR for a VFD. But just know that we can integrate all of these different offerings for controls with the USF. So we do Very Green. That's that top motor that's, 1 horse or less. We offer our ship loose VFDs. And then all of these options do integrate with Very Green. So that HOA controller there, it's so useful. Honestly, if you get your system set up with a VFD or you have an EC titanium motor, the interface for our HOA controllers, and maybe you can ask Chris for a better rundown on what that actually does, but really it's like a 12-page installation operation manual compared to a 200-page manual that normal VFDs go for. So it has a similar function to VFDs, just much, much easier to use. So just a quick rundown of what our Very Green motors entail. Again, this style is our true brushless DC motors. I'm not sure if you're familiar with all of our Very Green offerings. So these are the basic stats on this. I'm not going to go through in detail, but again, these do interface directly with the HOA. No VFD needed in between. These do have a single phase input. So be aware that our Very Green offering does offer single phase up to 1 horse. And then if you need 1 horse or larger, then it's going to switch to the 3-phase. So, and then this is our 3-phase EC titanium motor. This is our Very Green offering for the 1 to 10 horsepower range. So again, it interfaces with that HOA and all of the Very Green controls. Lastly, for controls on the USFs, on the IP fans, and also on our stack fan that I'm about to show you, is going to be the ship loose VFDs. We have the ACH 180 and the ACH 580 available with the USFs. So you may have seen like this basic style installation. So this was the installation that I'm talking about where contractors are very happy to have that inlet box. But what ends up happening is now the contractors have to go and source additional ductwork. They have to go and source a stack. They have to find anchor points for guy wires. I mean, that's a lot of work to do for our contractors and obviously for you that also design the systems. In order to roll all of that work into one package, we offer something called the fume jet. So these are a lower level fume exhaust fan, a lower level like vector lab fan. These are really, again, really useful. Getting that exhaust air up and away from makeup air units. They come in 7 and 10-foot heights. And what's really nice about these is you see the wires that are in that picture there. There's no guy wires on this. So very, very useful setup. Small footprint. And again, no need to run additional ductwork. You bring that duct right up to the fan. So here's the breakdown of that. Again, 125 mile per hour wind loads. Some areas might see higher wind loads than that. Like if you're in a region that requires like Miami-Dade in a way that if you're selling fans down in Florida, most likely not, but if you do, we do have additional high wind fans available beyond the 125 mile per hour loads. Everything that you see there is the full package, and we also provide the same controls, if not more, with those fume jet options. So, beyond that, now if you have an application that you're going to see some crazy temperatures, I had down in Arizona, a burn facility, the Mesa burn facility, had to exhaust 1,000-degree airstream. So in order to do that, an industrial process fan would be needed. So, and then that industrial process fan was made, or they actually had several of them, made out of fully stainless steel. So, and then we changed the configurations of that so that the motor's even farther away from the scroll. There's heat slingers. So a whole lot of applications, even beyond that. We list dirty air in the list here. We're talking about particulate in the airstream, or maybe they actually have to move something through the airstream. We had a paper shredding company that actually wanted to move paper, like the shredded paper, through their ductwork. This fan was able to do that. So these build pressure really well, and again, can handle all kinds of industrial process type applications. So now, going into that, I know that Blake had hit on stairwell pressurization. So fans that I've seen used for stairwell pressurization kind of go along with that UL listing for the heat exhaust. So, or excuse me, for smoke exhaust, for emergency smoke ventilation. So sometimes they do need that UL listing, sometimes not. But USF is a perfect fan for that. Again, because it does have the option to build a lot of pressure. They are meant to be outdoors. And then you can change the configuration of that discharge. So if you need to discharge in a certain direction. So yeah, with the other UL listings we offer on the USF, we have the restaurant exhaust available. Applications for restaurant exhaust can sometimes get to be high pressure if they're using a pollution control unit. So if you have a big bank of filters that's filtering the air, or a scrubber, that sort of thing that's going on the restaurant exhaust system, the USF is an excellent choice for that, because if those filters start to clog, maybe you're seeing 5 inches of static pressure through those filters in order to maintain the same CFM. So again, our fans do come with the controls, so you can do a set point with them in order to maintain a certain CFM or maintain a certain pressure in that system. So we do have the selections available for the UL restaurant exhaust to go with that as well. Thinking about some other applications as far as the smoke exhaust goes, I did come across one. This was in Nevada, and we had some pretty large USFs on the roof there that were meant for emergency smoke exhaust for, like, it was a Celine Dion concert. So very interesting. So they went through and had to do like a check on this and make sure all the fans could actually exhaust the amount of CFM. Some of the fans needed to be upgraded. So in order to move more CFM, so that was actually pretty easily done with that belt drive configuration. So that's, I guess, a benefit of a USF that's belt drive. You can upgrade the motor, you can upgrade the drives to provide the air that's needed. So I think with the emergency smoke, with the UL smoke, that is always tested in the building. So if it is ever short on air, I would say choose a belt drive for those emergency smoke applications. So I have spark resistance listed also. Spark resistance, not the same thing as like an EXP motor. We're not talking about explosion proof here. So we're talking about the airstream actually being non-ferrous, so non-sparking. So we actually will make parts of the airstream, if not the entire airstream, out of aluminum. Those levels, those different levels of spark resistance are based on what is actually needed. So if you're exhausting maybe a storage room that stores, some solvents or some other sort of chemicals, maybe your spark resistance requirements aren't as high. So then you'd go with like a Spark C. Spark C would be just the inlet cone of the fan, is going to be made out of aluminum. Spark B is the next level up. So now with Spark B, we would make the wheel out of aluminum. Spark A is the highest level of spark resistance. That's that entire airstream. So now the entire scroll, the entire wheel, and inlet cone are all going to be made out of that non-ferrous, non-sparking material. Lastly, on this slide, I did want to talk about sure air flow monitoring. Flow monitoring is kind of becoming much more common nowadays because everybody wants to modulate their fans based on flow in the system. So if one portion of the system changes to accommodate more air or maybe more cooling, that means the rest of the system has to react equally. So sure air is a way to measure that airflow without putting probes in the airstream. It will also help when test and balance comes out and they come out and say, oh, well, this fan isn't getting the air we need to the system below. Where when test and balance comes out, they go and drill holes in the ductwork, or they put probes in a really weird spot in the airstream. And it's just their measurements don't come out to be what the fan is actually doing. So all of our fans are AMCA certified, so we know what our fans are going to do. And I'll talk a little bit more about AMCA certification here as well. But basically, sure air is a piezo ring that goes around the inlet cone that has ports in it, that we can actually take a pressure from, and then we take a differential pressure on the outside of that fan. That differential pressure plus an area we use to calculate the airflow in the system. Test and balance can come out and hook up their transducers right to our fan, no problem. And then we do have a calculation that they would use with a K factor to get the flow monitoring, or excuse me, to get the actual flow of that fan. With the sure air and with us standing behind the performance of our fans, we do AMCA testing. So this is actually, like I was telling you at the beginning of our intro here, this is the facility that's actually behind me now. This is how we test our USF fans. So we have the air certification, we have the sound certification, we have the perfect setup. This fan, if you didn't know, AMCA testing requires you to test the fans every 3 years. So we are constantly testing fans on our air chambers. This setup in particular, like I said, is ideal. So we are going to get the best performance possible. We're going to test it here in our facility. The same fan gets sent down to Chicago and gets tested by AMCA and verified there. So we do every 3 years is likely a different size fan. We don't have to send like all the sizes in 1 year. That would be a little much, but it's to verify that, number one, our fans still perform the same way that we said they're going to perform. And in that, it means that our quality is being upkept. Our geometry of our wheels and of our cones are being consistent in that. So our fans do perform, but what you'll find actually happens in the field is this. So if you do get questions on why fans aren't performing in the field, it's due to something like this. So these installs create some crazy system effect. The first picture, as you can see, it doesn't have that nice flow into that inlet cone that I'm talking about. 3 wheel diameters normally is what you need. Here it's transitioning down into, oh my gosh, it's a few inches. So, and it's taking a turn directly in front of the fan. So you're basically cutting off 80% of the airflow there. If you can design a system with the nice 3 wheel diameters of straight ducting, and the same goes for the discharge side. So this fan, and I know Chris kind of hit on in the beginning. Yep, I knew you wanted to talk about this one. So Chris talked about choosing the right direction of number one, rotation and discharge. So the second fan really highlights choosing that. So right now with the airflow, the second fan, the discharge, that air wants to continue in that, scroll shape. It wants to continue flowing in a circle. And instead of allowing the air to continue in that direction, boom, they're breaking the back of the fan. So I don't know if you've ever heard that term. This is breaking the back of a fan. So with breaking that back of that fan, you're going to probably decrease your airflow between 25 and 40% right out of the gate. And that's when, again, test and balance comes out and says, where's my air going? Well, this is where it's going.
As a rep, one of the first questions we ask when we get a test and balance report is send me a picture of, and then sometimes we get, well, there is no picture, it's on a roof, it's inaccessible, or it's behind a hard ceiling, we can't get a picture. And oftentimes we see things like this, and this is an absolute killer. Again, so focus on your discharge orientation, because in this instance, had you done a reverse rotation of the fan wheel and did a top angled up, or even in this case, a bottom angled up, you could have turned that hard 90 at least into a not quite as bad, but still bad 45-degree, kind of breaking the back. So it's still not good. It could be better, but this could have been a much better performance. And to your owner, what do you do to fix this scenario? You speed up the fan, you use more motor power, assuming you have enough horsepower available. You might have to buy a new motor. But no matter what, the owner is paying for that loss, that volume loss, that pressure loss that's being generated there. And I think I saw somebody comment, Sam. Yeah. Thanks for mentioning that, Sam. So Greenheck does have a live system effect demo. It's probably one of the more impactful things. And Sam heard me say this. That's a demo that has nothing to do with Greenheck. That is just fan physics. It applies to every fan manufacturer. We take a small utility set fan and we put different duct connections. We show some that are, how AMCA test the fan, so you can see kind of a baseline performance. And then we put really, really bad duct connections, but really common things you see in the field. We are running the fan at a constant RPM, and we take live pressure and volume readings. So we're not adjusting anything to the fan. We're just making adjustments to the duct work, and it is crazy how impactful the duct is on the fan performance. And I think it's something that everyone takes home. Sam clearly remembered it. It's impactful, and if that's what you learned from the trip, then we're doing our job, right? Because that's something Sam's going to take forward on every job he works on going forward. So Elizabeth saw me pop on the screen. This is a big focus of mine in helping engineers design. All right, I'll be quiet now. I'll let you take back over.
No. I was glad that you popped in there. So really the only solution that needed to happen with that second fan would have been to choose it for a counterclockwise rotation. So when you're looking at rotation here, I don't know, can you guys see my laser pointer on there, Chris?
You can. Yeah.
Okay, awesome. So this fan, you can tell by the shape of the scroll, which way this air flows, right? So the scroll is always going to guide you. You're never going to go backwards and try and go out this way. That doesn't make any sense. So you know that this is a clockwise fan. So if they would have chosen counterclockwise for this application, that air could have just easily gone up and just flowed, boom, right into that turn. So again, choosing the correct rotation, choosing the correct discharge right out of the gate. If you need any help on that, just let us know. Let Chris knows he's an expert on this nowadays. So yeah. All right, before we transition into the plenum fans and we're really just gonna focus mainly on fan arrays and what we have there. If you guys have any questions, go ahead and put those in the chat. But I will jump right into our fan evolution here. So plenum fans, and I'll show you a few pictures of these applications. I'm not going to leave you hanging if you guys don't know what a plenum is or you haven't seen one. Basically, we're talking about air handling units. We're talking about rooms that are, sometimes there's just a plenum room, like where they had a big fan, or some of these straight vane axial fans in there. They went from vane axial to these big double wide. Again, these are in the basement in boiler rooms. Moved on to a little bit smaller footprint. So these are more traditional plenum fans. Again, it's basically moving air from one space to another. A plenum is a box that's pressurized, and that pressurized air will flow and can feed entire buildings, skyscrapers, that sort of thing. From the belt drive, we transition to direct drive fans. That's most likely what you'll see pictures of for retrofits nowadays for air handlers anyway. And now we've moved on to fan arrays, and so much more benefit and redundancy, efficiency is coming from all of this new technology associated with fan arrays. I know fan arrays are associated a lot with data centers, but what we've been seeing sweep across the country right now is retrofitting air handlers. So going through just some fan array advantages. I talked about the redundancy. There's smaller wheel sizes, smaller motor sizes, easier to change those motors out. I mean, imagine trying to change out a 100-horse motor on this big double wide guy over here. Like, some of those have just giant motors on them, where these, you have your small individual motors, or in the case down at the bottom, sometimes you just change out the motor fan in this one panel there. So shorter axial length on these pancake style motors. So these are the true EC motors out in the market today. The efficiency on those, again, amazing. We're going really in a good direction with all of our fan array applications. So with fan arrays, we also still do see a demand for these, I guess, building block style fans. I kind of call them Lego fans. So these are our HPAs, stackable, easy to move into small spaces. What we see with air handlers, again, is that they build either a room around a fan, or they have really small doorways leading to the fans. So you need a way to get into those doorways as well. So HPA has a little bit more benefit with sound attenuation. Applications will see HPA, again, that stands for housed plenum array, used for like hospitals. So those are really the sound sensitive applications. This has 2 inches of insulation all the way around it, plus perforations. So you'll see a 3 decibel decrease in sound compared to other fans moving the same amount of air, that 3 decibels is audible to the human ear. So when you talk about decibel levels, if it's anywhere less than 3, you won't even notice. 3 decibels actually means that it kind of explains it here that the sound from the fans, if there's a number of fans, actually would be doubled if you didn't lose that 3 decibel or 3 decibel decrease. And I talked about internal isolation with these as well. Isolating a fan means that you are stopping the vibration from becoming a sound elsewhere in the building, right? All right, so looking at our housed array, pretty simple setup. We have controls again for both available. We actually just came out with controls for our housed array to interface with those EC titanium motors. You can see those motors in there. Those are the style that have the built-in VFD in them. They're 1 to 15 horse available. So really, you could pick either depending on the application. So what I like about this modular unhoused array, so this is the MOA. I'm going to show you some slides in the future, but this can fit in a lot smaller spaces. Sometimes it's just that much easier and easier to set up as well. Let's take a look at that here. So comparing housed to unhoused, first let's talk about airflow. So fans in an array will have communication. Sometimes I refer to it as translation. There has been no AMCA testing on fan arrays up to this point. So really we're kind of going it alone in the market as far as putting fans in an array and then hoping that, you know, what is spec'd out is actually going to produce the air that is being required. So that we weren't guessing anymore. And since AMCA didn't do the testing, we actually did the testing. So with this, we actually set up some horizontal spacing and vertical spacing to see what the effects were. So when I'm talking about translation, here, I'll go back to that other picture. So basically, we wanted to see what would happen if we made these wheels closer together or farther apart. So that testing and performance resulted in us testing about 450 or 480 different configurations. So pretty intense. This is kind of a look at what that configuration looked like in our shop, again, in the Innovation Center behind me there. So as they did one test, they kept moving the fans farther and farther apart, and we're able to test the airflow as they continued changing the spacing on them. So that means with these tests, we tried different rotations, counter rotation, same rotation. Apparently it took 3 months of testing. This was a little bit before I actually joined Greenheck, but they got some excellent results. And those results now resulted in our optimization tool for our MOA. So if you want to go the open array route, we do recommend going with the MOA. You don't have to build any additional structures with this. Some of the traditional plenum fans, there needs to be a structure actually in place prior to this. So this model gets shipped broken down, and when it's actually selected, or when we do the selections, we take into consideration how far this actually ends up spacing fan to fan. So
I kind of wanted to chime in. I know that there are some engineers viewing the presentation, and I know their firm last summer kind of built around. I don't know if they realized the MOA was a new option, and they actually built design their own structure, use the Greenheck APMs, which are just the standalone fan, which is nothing wrong with that. But you kind of had to do some design yourself. I think the MOA in its current form and function was pretty new. So it could have been my job as a rep to make sure they knew about it. But in this situation, we could have just said, here's the opening, here's the airflow, here's the static. And Greenheck could have constructed this modular, quick field built up system, all designed and optimized through the CAP software. So that particular firm didn't do anything wrong. They probably just did a little extra design work than they needed to if they were aware that the MOA was available. Again, that's on my fault as the rep for not letting them know that that was a newer option we had available. So I really love the MOA for these applications. It's great.
We're not gonna blame you. We're not gonna blame you, Chris. I'm gonna blame our product manager that has now become a regional manager. So someone to blame there. But yes, the optimization tool, you tell the program your height and width of the opening that you have available. Sometimes we even encourage the customers or our engineers and our reps to design or open the space or make the space smaller depending on what type of airflow you need. Sometimes you don't need a really giant wall if you're not moving that much air, right? So we can help with the design of that. It just needs something solid to attach to, but we provide all of the hardware, all the panels that you see there. So let's just look at a quick example of what that wheel spacing does here. So here's an example of a 7,000 CFM at 3 inches of static pressure. That's our one wheel. That's the brake horsepower required to spin that wheel. So now when we put 4 of them together, we have 28,000 CFM at 3 inches of static. And with the spacing of 96 inches apart and wide, we have no translation, no communication happening, no losses happening from the air kind of bumping into it, the air coming off the other wheel. Now, when we start decreasing that, 44 inches is where our testing led us to start seeing some changes in that fan performance. So now as the wheels get closer and closer together, look at our brake horsepower went up here. So that's because we had to spin our wheels faster to get the same amount of air. So the goal is to maintain the same amount of air as we make our space smaller, essentially. So last example, 22-inch wheel. So 44 inches meant that we had 1 wheel diameter between each. 33 inches means that we have a half a wheel diameter between each, or just about that. And look at our brake horsepower increase down here. So now we need 10% or 11.1% more power in order to run the same CFM out of those 4 wheels. So the spacing between them does matter. If you go or had other competitors of ours say it doesn't matter, it is not true. Entirely not true. It does matter. So beyond, I know I've been really hitting on the air handling units, but we do supply these same MOAs for large scale fan array applications as well. This is just an example. Each of these is a 12 fan array. We can actually go double the height with these now. We can stack these fans 8 high and as many wide as you need. This one's doing 1.2 million CFM with 144 fans. So pretty neat, pretty intense application there. So just a quick look at maybe why we would want to go to the MOA here. So the brake horsepower is really what stands out to me here. So the MOA tends to be about 10% more efficient when we're talking about a 4 fan array, right? Once we get more and more, think about adding, 8-fan array in that, we're going to end up saving more in the overall cost for operation over time. So that's where, for me, the big savings is going to be initial cost is slightly less, and over time, your MOA options really tend to stand out. So I did some pretty deep dives into comparing an HPA and an MOA. The MOA's efficiency is always just outstanding. So here's those retrofits, or some applications of the retrofits I'm talking about. These dusty, rusty fans that you'll see in basements. So they're sometimes located in the basement, sometimes on a roof in a parapet in a penthouse, or they're literally inside the building. So these can be easily taken out. Normally they're torched out, and then the entire wall, an entire wall can be constructed in their place. So here's kind of the breakdown of what that MOA looks like. We supply all of these panels. We give you directions on how it goes together, and honestly, it goes together really quickly. I like to, and I told Chris this story before, we had an array going in down in Atlanta. We didn't have stickers on the fans to tell them which way the air flowed, so they installed the entire array backwards. Good thing they figured it out, because they were actually able to disassemble and reassemble that array in the correct direction in 2 hours. So that's because all of these fans actually link together via a Molex style plug. There is one point that high voltage needs to be landed to, and then our low voltage panel, that's our control panel, will control the entire array from one point. So it's really just a slick setup. This is just a quick overview of what our controls are looking like here. So again, that high voltage panel, high voltage is landed, and I don't see our inlet on this, or the inlet where they're landing the voltage, but basically voltage landed to one point inside of this panel, and then each of these distributes the needed power to each fan. In that same wiring will also provide, this is our control panel here with a Corel controller. In that same wiring, we will also have the 0 to 10 signals that each fan would require. And then we do offer a touch screen as well. So the touch screen is useful. It'll keep track of if maybe one of the fans goes down, or if you wanted to modulate a different set point. So we do have Sure Air built in to all of these fans. A lot of times they'll just put a certain set point for CFM or static that they want to keep the system pressure, or excuse me, the system pressure set to. Otherwise, if you do have a BMS, it will integrate with Modbus BACnet capable as well. So this is what it looks like when we ship it out. So you can see all the pieces are nicely stacked up and assembled. The fans, this one doesn't have a picture of the fans in it, but the fans are stacked in pallets as well, and shipped out and labeled. Each of these pieces has labeled, we actually do it A through K, I believe. So each of these is labeled with an A through a K so that they know where to go. Just refer to the original design drawings. Again, all the hardware is provided, all the junction boxes are provided, even the Sure Air tubing. Again, we're providing the entire package. This is what it looks like, an example of what one looks like installed. These are our older model fans. We actually do have our new CPF fans that are going in place of these blue style fans. So our new CPF model is just integrated into our MOA. our CPF actually has some new printed circuit board, or excuse me, printed stator technology. So it actually has, its stator is a printed circuit board, and it has permanent magnets in it. So some new technology that Greenheck is bringing to the HVAC community there. So another view of that install that we had at UMPC or UPMC, sorry. All right. Some last things to consider. So with the HPA or even the MOA, we talk about blank off panels and backdraft dampers. Honestly, everybody wants to add dampers to these fans. And we're like, no, please don't do that. So this is the reasoning why. So let's just take a look at this. So with fan RPM with a damper, or without a damper, fan RPM with a damper. Got it. And then we have, since we're speeding this fan up, our brake horsepower is higher. That means we're going to be using 3.1% more power just by adding a damper in front of a fan. So if you think about that over the course of, I mean, the longevity of a fan array, of arrays going in 6 years per motor minimum, and you can still upgrade the motors and change out wheels if you would ever need to do that. I haven't ever come across that being an issue. But these arrays are meant to be in there for quite some time. So if you think of per year, per fan, and you had however many fans we had here, like we're talking, we got there 16 or 16. So yeah, that's 24 fans. Oh, okay, I did the math for me right here. So 24 fans, the damper cost across the board, plus your brake horsepower increase cost. So over the first year of operation, just by adding a damper in front of each one of these fans, you're increasing the overall cost by $15,000 for 24 fans. So you might have more fans actually in the application, or multiple arrays, multiple air handling units that use way more fans than that. So really, the reason why I say no damper is because we've actually tested this as well. So in all that testing, we tested dropping a fan out of an array. What we found is that there's only a 6 to 7% backflow through an opening. So if we lost this fan up here, we'd really only lose 6 to 7%, and the rest of the system would ramp up to cover that 6 to 7%. So there's alarms that go on when a fan does go down, or you can just go ahead and pop in a blank off panel there if you're waiting for a fan to come in. And again, then you'd have no backflow happening. So I think allowing some sort of backflow, allowing the system to ramp up as opposed to spending $15,000 for dampers, really kind of a no-brainer in that sense. So I hope that kind of makes some sense to you guys. I know sometimes you're just going to have dampers, especially if you're going to shut down the whole system. That's fine. You can put a damper wall in. Obviously, some of our applications, they have louvers. These could be damper walls. But really, in front of each fan, we don't really need a damper. That's my soapbox on that one. So just a quick look at our fan optimization array tool. Again, will pick out the right motor and RPM for you as well. So you don't have to go about doing the calculations to see, oh, am I going to be underspeeding or overspeeding? When it comes to this sort of array as well, underspeeding, overspeeding, you don't have to worry about that because this is a true EC motor. And I know we're getting close to on time. I saw you pop up there, Chris. So I'm just about to the end here. I just had a few things to talk about just to show you some motor technology that's out there with these motors. Did you want to comment on anything before that? Okay, I
Go ahead and go
gotcha.
over that. That's fine.
I gotcha. Um, so our MOA tool is going to choose the right motor for your application. It does also allow you to choose quantity as well. Sometimes, I mean, it's easier to maintain less amount of fans, so sometimes it's better to go with the larger fans because it's less quantity, but you'll see some differences in price go along with that as well. And I just wanted to show this slide real quickly just to show you down in the bottom here. This is our new printed circuit board motor. So inside of there is that laminated stator. So instead of stators normally have the big copper windings, what they've actually done here is laminated really thin strips of copper into like a circuit board. So there's a computer that basically turns on those different windings on and off, just like a normal AC induction motor. And so this actually tends to be even more efficient than some of those blue fans, more efficient than some of the other motors in the market that we're offering here. So I'm really excited for our CPF to be integrated into our MOA. I'm expecting that to occur here in April. We'll be doing some pre-sales as well. So if Chris is interested, or if gets interest from you in pursuing some of these fan array technologies, definitely reach out to him and let him know. And that's about all I have. So I hope you guys enjoyed the prezo. I know I went a lot of different directions. I hope I brought up some good applications for you. Anything else to add, Chris?
No, I mean that motor, I've been lucky enough to see one in the testing station, and when you see what a normal 7.5 horsepower motor looks like compared to the new one, it's remarkable how much smaller and I think a little bit lighter that it is. To be fair, I don't know if I picked it up. It just looked like it was lighter, but
Yeah.
it's remarkable how
Oh,
much
they are.
smaller it
Yeah.
was. And again, the
Yeah.
smaller it is, the less that's taking up air, right? It's less impedance on the airflow, less pressure resulting in the system.
Yeah.
If you were joining us before the top of the hour, some things to remember. Focus on your discharge orientation, your wheel rotation, right? Whether you have an up blast fan or a clockwise or counterclockwise or bottom angled up, top angled up. That can have a huge impact on your system design, your system pressure. It can save a lot of headaches. So always keep an eye on that. Elizabeth touched on caps. Caps will often lead you to the right fan. So allow it to do that for you when we're talking about the different levels of classifications you can order. We have a system effect simulator on ECAPs. If you go to ECAPs and go to your fans, you can kind of see the result of some of those bad duct configurations as well. And then touching on that, I think, Elizabeth, you probably know the number better than I do. Is it something like 80% of fans are ordered as up blast and clockwise orientation? People say,
Yes.
why is that? We say that's because that's what the default in caps is.
Yes.
So,
Yep.
We'll select fans and, if it's a small fan, maybe it's not a big deal. We can make some adjustments in the field. Like 80% of fans are ordered as the default setting in caps. So I think it's really important to take a look at that. And then obviously also the, everyone should remember all the new fan array options, the house pump array, it's newer stuff that we're getting everyone to know about that. So we're at the top of the hour. Thank you all for joining. I know people sign off to go join their next meetings or go grab some lunch. If you would like a similar presentation this for your firm, please let us know. If you have any project-specific questions, send them our way. Send them to Scott, myself, Blake, Nick, and we can get in touch with Elizabeth and her team and see what we can work out for you. I'm really interested in doing the MOA with those new motors and fans myself. So with that, Elizabeth, thank you for doing this for us, and thank you all for joining, and I hope we see everyone next week.